Well, hello, physics. Welcome to a lecture on circular motion. So we're looking here not at linear motion, but at circular motion. This is the first lecture in chapter 7 of your textbook. We'll be doing one on each of the lettered units within the chapter just to make sure that we cover everything in detail. Okay. Circular motion has a lot of the same terminology and concepts as linear motion. You still talk about velocity and speed and displacement and acceleration, and all of that is true. We're just looking at circles now instead of straight lines. So you'll hear a lot of similar terminology, and you'll recognize a lot of the equations as being the same sorts of ones that you looked at with linear motion. It's just that we're now having to talk about parts of a circle instead of a straight line. Okay. Two things we need to define real quick is the difference between a spin and a revolution. So if the axis for the object for the spin is in the object, and it's spinning. My hand is spinning on the finger. If the axis is not in the object and it goes around like this, then that's a revolution. So spinning, the axis is within the object. Revolving or revolution, the axis is not inside the object that you're tracking. Okay? Quick, good example of that is our solar system. The moon spins on its axis and revolves around the Earth. The Earth spins on its axis and revolves around the sun. And so those are just some examples of the difference between a spin or a rotation. Rotation and spin mean the same thing, and revolution, where the axis for the circular motion is not inside the object that you're tracking. Okay? So displacement. Displacement in a straight line is the difference between your location on a numbered line between 2 points in time. Two-dimensional displacement, still a straight line concept where you have difference between two vectors, and you subtract the vectors and you get a resultant, and that is the displacement, right? Here, it's a very similar idea, but the coordinate system is always measured from the axis, okay? And we always measure in radians. And so we're looking at the kind of arc that the object makes as it moves in a circular motion. And we don't use degrees, we use radians. Now, we didn't do a whole lot with radians in geometry, but you do use radians a lot in Algebra 2. So hopefully you're coming out of a discussion with radians in your recent math history and you're comfortable with that. But just to reiterate, there are always 2 pi radians in a circle. So to go from one point in a circle all the way around and back to the same point, you've got a 2 pi revolution or rotation. And then if you go halfway around, then that's pi. And if you go a quarter of the way, that's half of pi. And an eighth of the way around the circle would be a quarter pi. Okay, so these are things that you've seen, I hope, enough to become familiar with them. I'll show you pictures of that in the next slide. When you're looking at linear speed, you're talking about the distance of the path that you took divided by the amount of time. For a circle or for circular motion, we're looking at the size of the angle that you created in a unit time. Okay, so you're moving in a circle. We're not caring about your actual path. We're caring about the measurement of the angle inside the central angle there, inside the circle. And again, we're looking at that angle with regard to radians, not in degrees. Okay, so let me show you some pictures for that. Radians are a radian is the length of the radius of the circle laid out on the circumference of the circle. So the length of that arc equals r. The degree there would be 1 rad, 1 radian. Okay. There are 2 pi radians in a circle, so we just label them in terms of pi. We don't bother doing the math. Okay. So to go all the way around is 2 pi. Halfway around is 180 degrees, but it's also pi. Okay, a quarter of a circle is 90 degrees, or half of pi. 45 degrees would be an eighth of a circle, or a pi over 4, fourth of pi. Okay, and then so all of these points can be represented either by a degree or by a radian statement. And don't freak out, keep calm, set calculator to radians, and you'll be okay. So let's do a little bit of math with that. We're going to be looking here at the speed of this common carnival ride. And if I wanted to know how fast is this rotating, one of the things that I could do is look at the degree that was created by by the circle moving through in 1 second. And let's say it went from this bar to this bar in 1 second. It's a pretty slow carnival ride, but just for the sake of our argument, I could then measure this angle in radians, and that would be that many radians per second, and that would be the angular speed. Okay, we're going to do some actual math sort of stuff with this clock. If I wanted to know what's the angular speed of the minute hand, and I was told, just in case I didn't know, that it makes 1.0 revolutions every hour. Well, that's obviously what happens with a minute hand. It goes around in an hour. I could turn that information, 1.0 revolutions per hour, I could turn that into radians, and I just have to do some converting of terms. Hours into minutes, minutes into seconds. Okay, so that's easy. Revolutions into radians. 1 revolution is 2 pi, because all the way around the circle is 2 pi. So I multiply across on the top and on the bottom, and I have 2 pi divided by 3600, or 0.0017453 rads per second. And so I wouldn't want to leave the number like this, because I was only given 2 significant digits. So 2 significant digits, and I use scientific notation to express my answer as accurately as I can. 1.7 times 10 to the negative third radians per second, or rads per second. Okay, that would be the angular speed of this minute hand. Pretty darn slow. And that's, just the way that that works. Obviously, it would be even a smaller number if we were to look at the angular speed of the hour hand. That takes 12 hours to make a revolution around the clock. So, circular motion also has a concept in it called tangential velocity. Tangent, you see the word tangent in there, and a tangent is a line that touches a circle at exactly 1 point. And so a tangential velocity is a velocity measured in a straight line as an object moves through the arc of the circular motion. So this comes into play more often when an object is going to be released from circular motion and fly on, like throwing a rock from a sling, David and Goliath, right? The tangential velocity becomes linear velocity when that rock is removed. So you can think about it that way. That helps you clarify what we're talking about. It's a vector measurement, the direction of which is tangential to the circular path. Okay, so the vector touches the circle at 1 point. We calculate it as length of arc traveled per second. So angular speed was looking at the degrees that are swept out per unit time in the circle. Now we're not looking at the central angles, we're looking at the length of the arc, okay? And so you need to get the length of the arc by taking the central angle, again, in radians, and multiplying it by the radius, and then dividing that by however long that was that you timed it by your unit time. And that will give you your velocity. We do measure this in meters per second, and the radius should be measured in meters, okay? So let's look at that. Again, our carnival ride, the angular speed was looking at the central angle that's created per unit time. Here we're looking at the vector that is formed when you tangent out this motion and looking at the speed that's represented there. And again, as I said, it's usually most helpful when you want to know how fast will something be going once it's released from its circular pathway. So this guy's got a 1.5 meter long sling. This is about how long the slings would have been for actual warfare, not for children's toys. The slings that you might see for sale in toy stores are going to have a very short strap because they don't want you to get very much speed on it. But the ones that were actually used in warfare, 1.5 to 2 meter long straps that would put a whole lot of velocity, a whole lot of momentum into that rock. And it kills people. That's the point. So this guy has got an actual weapon sling here, and he's slinging that thing around, and it has a tangential velocity here. And at some point, he's going to release half of that strap and let that rock go, and then the tangential velocity will become, a linear velocity, and that's the way the rock's going to fly. So if you wanted to analyze that and do some math and try to calculate how fast is that rock going to go, we can look at this here. So here's the formula for tangential velocity. 1.5 meter sling. the angular speed is 4 pi per second. So he's making 2 complete revolutions every second. So 1, 2, 1, 2, and that is that's a good swing to get that long of a strap going. Okay, and so you take the radius of the circular motion, 1.50 meters, and the angular speed, which is 4 pi, divided by the unit of time per second. 1.5 times 4 pi times 1 second. 4 times 1.5 is 6 pi. 6 pi is 18.849. And then per second, wait a minute. Sorry, 18.849 meters per second, and then I just need to correct for significant digits. So 19 meters because I only had just a couple of sig figs, and actually I could have gone an additional sig fig there. I should have gone an additional sig fig. No, I shouldn't. 4.0 pi. There you go. That's why. Good morning. 2 sig figs, and we move on. Alrighty. Circular motion. Circular motion results from the direction of tangential velocity constantly changing. So centripetal acceleration. Centripetal, you might have heard of centripetal forces. We'll get into that in the next unit. Centripetal forces are what cause centripetal acceleration. Here we're looking at the acceleration on the rock in the sling, and it always faces the center of the circle. Centripetal acceleration is always towards the axis, okay? And it's calculated as the square of the tangential velocity divided by the radius. So I just showed you how to get the tangential velocity. We now use that, we square it and divide by the radius, and that will give us this acceleration, also in meters per second, okay? Actually meters per second squared, because it's acceleration. Or if you have the angular speed, you can also just use the angular speed divided by the square of the radius. They'll give you the same number, okay? Either of those will get you the same thing. So if we're looking at centripetal acceleration, then here we're talking about the fact that the crust of the Earth is being accelerated towards the center of the Earth. The crust of the Moon is being accelerated towards the center of the Moon. The Moon is being accelerated towards the Earth. The Earth is being accelerated towards the Sun. And all of that is done because of the change in vector here of the tangential velocities changing all the time. That causes acceleration, and we measure that with this centripetal acceleration. So now I want to know what's the centripetal acceleration of the rock. What kind of force is holding this rock into this circular motion right now? And the straps are providing this force. So what kind of acceleration is going on towards this guy's hand with the rock? So it is Vt squared divided by r, okay? So we have 19 meters per second squared. That's given to us where we solved that from the last question. And the strap is 1.5 meters long. So 19 squared is 361 meters per second squared, right? Divided by 1.5 meters. And then you do that math, you square this, and you get this really cool number. And then you divide by 1.5, sorry, you square this and divide by 1.5, and you get this really cool number. And then we need to adjust for significant digits. So 240 meters per second, and that should be squared, meters per second squared, because it's acceleration. So the tangential velocity squared divided by the radius. That's all you got to do. Angular velocity. Angular velocity is a related vector concept to angular speed. And so just like velocity and speed can be the same thing, but not always, because one is vector and one is scalar. The same thing here. Angular velocity is also looking at how many degrees of arc are you sweeping out per unit time. But this is a vector measurement, not a scalar measurement. So you can't draw a vector that changes its direction. By definition, that is not a vector. So we use something called the right-hand rule when we talk about the vector of angular velocity. And we draw a vector at a 90-degree angle to the rotation, and the direction of the vector tells us if it's spinning counterclockwise or clockwise. And it's called the right hand rule. So if you look at your hand, and I'm going to block my face here for a minute. If you look at your hand and you were to wrap your fingers in the direction of the rotation, your thumb is the direction that you draw the vector. So if I've got something spinning this way, okay, I represent that by pointing my fingers in the direction of rotation, and my thumb tells me to draw the vector up. Draw the vector up. If I've got something spinning the other way, going like this, I wrap my fingers along the direction of that rotation, and now my thumb is going down, and I would represent that rotation with a vector going down. Okay, so upwards vectors, vectors that go up represent counterclockwise motion. Vectors that go down represent clockwise motion. So you can keep that straight too. Okay, some examples there. This is just a picture of that in case my fingers in front of my face didn't make sense. If the object is going this way, you'd wrap your fingers going in this way, and that makes your thumb point up. And so the vector for this measurement is drawn going up from the rotation. And there's another picture of it. If the rotation is going this way, your fingers wrap that way, your thumb goes this way. And so a thumb points up for counterclockwise rotation, and it points down for clockwise rotation. Okay, so you can calculate average angular velocity. It's calculated the same way as the angular speed, but now we have a direction to it. So if we're looking at this leg, the leg at time 0 is here, and at time 2 it's here, and there's a 0.034 second gap as he flips his leg up, right? It's a 90-degree rotation, but that doesn't help me. I need it in radians. So first, we need to say at time 0, the right leg is 0 degrees relative to the horizontal. At time 2, it's 90 degrees relative to the horizontal, but I need radians, so he converts to radians. Now, if you can remember that degrees divided by 57.3 gives you radians, then that's great. Otherwise, you can do a conversion factor that says this many degrees, and then say that that's some fraction of 360, and then that same fraction times 2 for 2 pi. But it might be more convenient to just remember that you always take the number of degrees and divide by 57.3, and that'll give you radians. So we have 1.57 radians, and that happened in 0.034 seconds. So here we have 1.57 radians in 0.034 seconds, and so my answer is 46.2 radians per second. So that's the angular velocity of that guy flipping his leg up. Okay, and last slide. Circular motion also has angular acceleration and tangential acceleration. So we've talked about angular speed and angular velocity. It's always the central angle that we're measuring in radians. If you have a consistent speed, then you're not accelerating. But if you're rotating at a certain speed and then you either speed up or slow down, you've accelerated. And so we can measure angular acceleration exactly the same way that we can measure linear acceleration. It's the change in speed divided by time. So that shouldn't be anything new or hard to imagine. If you're going at a certain number of radians per second, and then later on you're going at a different number of radians per second, you've accelerated. Okay, so that's just a quick subtraction and division. Tangential acceleration is a little bit more complicated. You have to have already figured out your angular acceleration, and then you multiply that by the radius to get your tangential acceleration. So we're multiplying the acceleration at the axis times the distance that acceleration is out on a radius to give us the tangential acceleration. Okay, so this would be a guy swinging a rock at one speed in a sling and then starting to swing it faster. How much faster is it going? What's the acceleration that the rock experienced in a tangential direction? Figure out the increase of velocity at the angle and then multiply it by the radius. Okay, and that gives you the speed, the acceleration on a tangential direction. So lots of terminology, lots of equations. That's okay. We'll have lots of time to practice it this week. Ask any questions that you'd like in the comments field below, and I'll see you tomorrow. Have a good day. God bless you.